Okay, so today we're looking at the form of proofs of circle geometry. Now, what you need to understand here when you're proving is that for every step that you make, you must state a reason why you make that statement. So it should be supported with a reason. Now, we want to prove the center chord theorem, which is stated that a line from the center, it bisects what we call bisect the chord. So I want to see if it is true. Now, how do you prove that theorem? You have to construct. So you're constructing new lines. Construct OA, AO, sorry, and BO. So what you're going to do here, you are constructing new line. You're from what you are given, you're going to construct your own new lines. And now when you look at this is lines from the center. This OA and the BO are lines from the center, and both of them, they are radius. They are both radius. That's what you need to understand. Now, what we need to prove is to prove that this line here is perpendicular, and it has to it's perpendicular which is given, but now I want to prove that AP is equals to PB. Now what are you going to do here? You are going to what you call prove, show that AOP is congruent. So you're going to actually prove that these two triangles are congruent, meaning to say they are identical in size and shape. So how are you going to do that? You can see from here in triangle, these two triangles, what we have here, we can start with OA is equals to OB because they are both radius. Both radius. So both of them, they are radius. Okay. Then because it's from the center to the circumference. So okay, we will prove that one what is it? The side is one side is equal. Then what else can we see that we also in terms of side we find that OP is common. So both of them, they share OP. So this is common. Then what else can we say again? Is the triangle, the angles. So we can say this one P1 and P2. So P2, so we're going to say P1 is equals to what? P2, they are both equal to 90. And why is this? This one is given. So in this case, it's given. That's the reason, it's given. Now, so it means that if we have got an angle and two sides that are equal, if we've got angle and two sides and an angle that are equal, that proves that those two triangles are congruent. So therefore, we can now say O triangle OAP is congruent to triangle OBP. Why is it like that? Side, angle, side. Okay, side, angle, side. Then what else can we say? Is therefore we mean that OP is equals to PB. These two are equal, and we are now saying if these two are equal, it means that OP, okay, AP, sorry, not here, AP is equals to PB. Then it means that OP bisects AB. That's what it means. So this is proven. So that's the first theorem. But also in other cases now you'll be given that the line it bisects the chord AB. Already are given that, and also we have it's also perpendicular to the line here. From we don't know where it is, but we want to prove that it is from the center. So prove PR passes through the center. So it has to pass through the center. That's what we are saying here. So for it to pass through the center, again, we construct from any point. You can just put any point. Maybe you can put even T. So we're going to have T. Then I'm going to have again, you want to prove that this line is actually passes what called passes the center. We want to prove that it passes the center. Now, what are we going to do now? We want to see that we have constructed again the line here. This is what you construct. You construct this AT and also TB. Okay, then from there, what do? We know that AQ is equals to QB, and this is given. Okay, then if we are to say Q1 and Q2, Q1 is equals to Q2 is equals to 90. This is also given. Now, another thing here is that TQ is also common, is common. Now, again, this one satisfies what called a congruence triangles. So it means that ATQ is congruent to TQB. Okay, and this is side. Now, if it is like this, it means that your AT will also equal to TB. And now we are able to say that you have done the proofing. So in other words, we are saying all the points in PR, all points on PR are equidistant from A and B. So they are all equidistant from A and B. And also the center is equidistant from, that's what we know, from A and B. Therefore, PR pass through the center. That's what we have here. Okay, let's move on to the next next theorem. So this one is angle at the center theorem. Angle subtended at the center is twice angle subtended on the circumference. So what do you need to do here? You need to construct a line here. You need to construct a line. Can call this A to PT, put T here. Then what we are having here, we have got this one, let's call P1, call P2. Then let's also separate this one as O1 and O2. Okay, and now with P1 and P2 here. Now, what we're having here is that let's call this P1, let P1 be X and P2 be Y. That's what we are saying here. So we're going to put our X there and we'll put our Y there. But what we see is that from this center to there is a radius, from this center to there is a radius. So it means that it's an isosceles, this triangle here. Two sides are equal, and when these two sides are both radius, it means that you're going to have X here. That's what we're going to have there. So it means that what we're going to say, we are saying here, P1 is equal to X is equals to A is equals to X. Okay, because radius are equal, and this one gives you an isosceles. Now, here, so it means that, but now what we know is that O1 is equal to sum of these two. Remember, exterior angle is equal to sum of opposite interior angle. So O1 is equals to sum of these two, which is x plus x, which is 2x. Now, when we have got 2x there, it means that's what we have there. So for this part here, because remember what we said for the triangle, we are saying if we have a triangle like this, you must remember this, guys, this theorem. Triangle like this, if we have got p here, we've got x here, we've got y here. This p is equal to x plus y. That's what we mean by this. Because this is a straight line, it must give you 180, and this is a triangle, it must also give you 180. We add this to this one here to get, what is it, 180. We also add this p to the angle here to get what we call 180. So that's why we are saying these two are actually, you must remember this, what we call this theorem. Okay, what does it say? We're going to say exterior angle of triangle AOP. That's what we have. Now, then we move on again. We also see P2, same for P2. P2 is equals to B is equal to Y. Again, radius. They are equal, and it's your isosceles now. Isosceles, and isosceles is O what? OPB. Then it means that here we also have what? We also have Y there. Then again, we bring up the point again. O2 is equals to 2Y. Again, Y, exterior angle of OPB. Okay, that's what we have there. Then now, what we see is that we are going to say we have got 2x, OY is what? O1 is 2y, and O2 is, what is it? Is 2y, okay? Now, what do we do from there? AOB, how do we get AOB? AOB is equals to 2x, which is 2x, should I say, is equals to O1 plus O2, which is equals to 2x plus 2y. Okay, that's what we have there. Then it means that here it's going to be equals to 2 in bracket x plus y. Can you see that? Now, when we have got x plus y here, but what do we also know here? We know that p is equals to x plus y. P is equals to x plus y. APB is equals to x plus y. APB is equals to x plus y. So therefore, A or B is equals to 2 times APB. Okay, then that's how it is. It's proven. So that's how it is. It's proven. Your x plus y, we have it here. That's what it's saying. Then you are done with what you call with your proving. Okay, that's what you must remember here. You separate here, then you apply exterior angle is equals to opposite sum of opposite interior angle. Then you also deal with this one here. It's equal sum of these two here. So it means that here you've got 2y, here you've got 2x. That's what you're going to have then. Okay, that's what. So remember, you construct one line here only. Okay, then you'll be done. Now let's move on to the next one, which is angle in the same segment. They are equal. Angle in the same segment that are equal. Now we are going to construct one line here. We're going to construct a line that goes to the center. Okay. Then again goes to the other side there. G. Okay. Now we have got this angle now. But now can you see something here? We are applying, you must know that we are applying the previous, what is already proven here already. That's what we're going to do here. You're not starting from afresh for this one. Because what you're going to construct, you're constructing this one here, and it shows you that A or B should be equal to 2 times, did I say, sorry, can I just, it is your B the angle B is equals to half of A or B, because we know that A or B is twice B. That's what we know. So B is equals to, so what does it say? Angle at the center. Angle at center twice angle and the circumference. Now, here we have got also C is equals to C. Can you see that C also is subtended by the same chord? Remember, it's going to be half A or B. Again, the same reason, angle at the center theorem. Then now, therefore, it means that B is equals to C. And these are in the same segment. Okay, so it's proven here. So we are moving on to the next one. Okay, so here you are going opposite angles of a cyclic quad. They must add up to 180. Want to prove that one? What must you construct here? You construct the line that goes to the center. And touches the other side, the opposite angle. Let's call this 1 and let's call this 2, O1 and O2. Now, what we see that there is that we are going to say, okay, for us, we know that A or B is angle at the center and A, B, O is angle on the circumference. So what it means here, it means that this angle here, O1, is twice this. So let's call this Y. Let's call this angle BY. Now, when you name this angle BY, we are going to see that A or B, so let B equal to Y. Then we know that we are going to say O1 is going to be equals to 2Y. Why is it like that? Angle at center is twice 2 times angle at the what? At the circumference. Okay, now we know that O1 is equals to 2Y. What about O2? O2 is equals to 360 minus Y. Why is it like that? Angle at a point O. So angle at point O must add up to what called the 360. Okay, now, so how are we going to do now this one here? We want to find D. What is D now? How do we get D? We find that D, to find our D, angle D, we're going to say is going to be equal to, D is going to be equals to half of this angle, half of O2, which is equals to half of 360 minus Y. Why is it like that? It's because we are saying minus 2Y, sorry, minus 2Y here, minus 2Y here, sorry about that. This O1 is 2Y. Now, half of OY, so why is it like this? Is because we are saying angles at the center is equal to angles at the circumference. That's what we are saying here. And from there now, what do? We find that we simplify this one. Is going to be 360, it's going to be 180. If we take half inside there, minus Y. So therefore, it means that if D is 180 minus Y, D is 180 minus Y, it means that D plus B must give us 180. D plus B must give us 180. And also, therefore, as well, A plus C must also give us 180. Why is it like that? Because we know that sum of, sum of angles of quad equal to 360. That's what we know. So what should be the remaining here is 180. That's why we're saying A plus C is going to give us also 180. So this one, you're just going to state it, giving the reason. But where you need to prove is here. That's where you need to prove to show that, your angles, they are twice as those in the vertical on the circumference. So you can see that this is the very common theorem that you're applying. Angle in the center is twice angle in circumference. So remember to construct this this line. Now we're moving on to the next question, which is 6. Okay, for this one here, what do we need to do? We need to construct two lines. We need to construct two lines to the center. First, two lines to the center. Okay, then from there, we also need to construct the line that goes straight to OA. Okay. Okay, when we have that, remember what we need to prove here. We just want to prove that, you just want to show that OBA is congruent. That's what you must remember, guys. It's congruent to OCA. And it means that same in size and shape. That's what it means here. That's what we want to prove here. Same in size and shape. So now, how are we going to do that? We know that from this, we know that B, we can start, okay, let's start with OA. OA is common. Okay. Then OB is equals to OC. These are radius. Or the radius, then because it's coming from the center, then what else can we talk, can we see there? OBA is equals to OCA is equals to 90. Why is it like that? Radius perpendicular to tangent. Perpendicular to tangent. Okay, radius perpendicular to tangent. Then it means that therefore we have got one angle which is equal and the two sides that are equal, hypotenuse in the other side. So we've proved the the SS the right angle one. So we're saying OBA therefore is congruent to OCA, and the reason is side 90. Side 90. Okay, then therefore it means that your AB is equals to AC. So you prove that those tangents are equal through that. That's what we are supposed to do here. So remember here, you're proving that these two triangles are congruent. That's what you're just doing. When you do that, it means that your AE, AC, and AB will be actually will be equal. Okay. Then let's move on to the last one, which is the one for the turn chord. The turn chord. This is very interesting here. We are going to construct two lines here. One line that goes there, which is a diameter that passes through the center. Okay. Then the other line that the chord that connects there. Now, let's call this P, B, I've got label here, A and C here. Then let's call this P1 and P2. Let's also call this 1 and this one 2. And now let's call this whole angle X, okay? Now let's make it X. Let BAC B equal to X. That's what we are doing here. Now, given the tangent AC and the chord AB, okay, and the chord AB subtending an angle APB here, APB, what called an CP in the opposite side of what called of AB, okay? Now what we have now is that prove that A1, which is this, is equal to P2, which is APB, okay? Now, what are you going to do here? First of all, you're going to look at these triangles here. We're going to look at this here, this angle here, the whole angle here, that is 90. We're going to say, okay, let's make it this one D. So DAC will be equals to 90. And why is it 90? Because diameter is perpendicular. Remember, diameter is just twice the radius, perpendicular to tangent. We know that. Now, then again, is that DPA is equals to 90. We know that this is the angle in the same circle because we are considering this is a diameter. So angle in the same circle, we know that is, what is it? It's the what called it's 90. So angle in same circle. Same circle, angle in the same circle is 90. Then again here, what it means now, it means that if we are saying this is 90, this is also 90. What do we know? We know that if we say A1 plus A2, we get 90. And P1 plus P2, we also get 90. But if we are to look at these angles and hold our papers like this, okay, we see that your P1 and your A2, they are equal. Your P1 and A2, they are equal. Why? They are angle in the same segment. They are in the same segment. Looking at this as a chord here, they are subtended by the same arc. So we see that we're coming from here, we come back, we start again, same point, we come back. So this angle here and this angle here are actually equal. So what are we going to say? We know that we're going to say P1 is equals to A2. Why is it like that? Angles in the same segment. Angle in the same segment. Therefore, if these ones, the two of them, they add up to 90. We know that if these two are equal, it also means that A, P2, it will also be equals to A1. Okay, that's what it means. It means this also, because remember, we need to add A1 and A2 to get 90. We need to add P1 and P2 to get 90. And we are saying these two are equal. If these two are equal, it leaves these ones also equal. Okay, that's what we're talking about here. I hope you understand how we are supposed to what you call to prove as well and construct your lines. So these dotted lines are the ones that I have constructed. I will send you these notes so that you can understand much better looking at the what you call at the diagrams. Okay, so thank you so much. Now I think from now we're going to be attempting some questions, because if you follow all the lectures on the analytical, circle geometry, quadrilaterals, and also the proving, it means that your Euclidean is actually good now. And also there's the area thing that you need also to understand. I think there's a lecture on that, what called on the tree. Okay, thank you so much.